Bernard Price, at his time, the exciting technology that came around was electrical engineering, and guys were building 20 kV lines and maybe 100 kV lines and similar. Things that we almost regard as of no importance today. But those were the groundbreaking things that were happening at the time. Generators were installed. He became the chief engineer of what was then the Victoria Falls and Transvaal Power Company Limited. Interesting that even in those days, there was this vision of a Southern African grid. Because otherwise, why should they have called it the Victoria Falls and Transvaal Power Company? We're already many years past that point. Bernard Price became the general manager of that company in 1926. He became the resident director, which is the big boss in South Africa, and I guess there was some overseas shareholding of it in 1936. And he held that position till 1948, when the company changed into what was known then as Eskom with a C and not a K. And of course, we know that organization today as Eskom with a K. Ian General was making jokes about Eskom with a K a little bit earlier and saying that Wits has installed some generators, so you should not fear if there's a power interruption that might occur tonight. But Ian, if the generators doesn't work, then we will look towards Wits' accountability as far as the failure is concerned. So let's hope we don't have to test any engineering skills tonight, and we can just celebrate the evening. Ladies and gentlemen, Ian Craig started his education at an outstanding university. Of course, Pretoria University. He then went to MIT, the Massachusetts Institute of Technology, where he obtained a master's degree. And anybody that writes an MIT degree behind his name, you can see, believes that they're a little bit better than most of us that only studied at Pretoria and at Wits. And I'm sure you will see tonight the quality of Professor Craig. He obtained his PhD from Wits. So in that sense, Ian, we've got some things in common. We both studied at Pretoria and Wits somehow. He also obtained an MBA. In 1995, Ian became professor at Pretoria University. He's now the head of the Control Systems Group. He spent some time at Mintek, and I'm not going to delve too much into his career. I think some of that is going to be reflected in the presentation tonight.
So tonight I want to talk about automatic control, the hidden technology that modern society cannot live without. And hopefully by the end of this presentation, I'll have convinced you that that is true. So I'm going to try and do that. So one of the examples that I'm going to use is that without automatic control, one doesn't have modern aviation. The second example I'm going to give is without automatic control, we will not have any power. This is a picture of New York City from the Jersey side, if you're wondering. And then third examples I'm going to have a look at is you're very much alive with automatic control, and without it, then you're probably going to be dead. So those are three examples that I'm going to look at. This is our youngest a few years ago that came to Malaysia tomorrow morning. So the talk is structured as follows. I'm going to start with an introduction, just to give some indication of what automatic control is about. Then talk about the concept of feedback, and then talk about application areas of automatic control using IFAC as a structure. And then I'll categorize the examples that I'm going to present in a categorization that's at least makes sense to me and hopefully to you as well. Then the examples that I'm going to present are some mechanical systems, because they're very visual and people can relate to them quite easily. I'll talk briefly about electric power systems, And then I'll give an industrial control example as well, which is grinding mill circuits. And then to show that you don't have to have a physical system to apply these concepts, I'm going to talk about personal finance as a non-physical system, but still engineered. And then I'll close off with two examples from biomedical examples: glucose homeostasis in the human body and HIV/AIDS therapy. Then I'll conclude with some trends impacting on the automatic control field and on a lot of other fields as well, and then give some concluding remarks towards the end. Right, so what is the definition of automatic control? This is from Professor Wikipedia. Automatic control is the technology by which a process is performed without human assistance. And then goes on to say that automatic control is operating equipment with no or minimal human intervention. And automatic control is very heavily based on the concept of feedback. So let's look at the concept of feedback. When people think about feedback, you might think in terms of a survey that's done. Were you satisfied with some service? Were you agnostic to the service, or were you dissatisfied? Automatic control, this is not good enough just to say that you were satisfied or not satisfied. You actually have to do something with the information. So, and in automatic control systems, feedback is information obtained from a system used to change its behavior. And that's a crucial concept in feedback. For those of you who've done some automatic control courses or control courses at university, feedback control is also known as closed loop control. One has to close the loop from giving your opinion and actually doing something about it. And the main purpose of feedback is to counteract uncertainty. Uncertainty in the model of the system that you're trying to control, uncertainty in terms of additional signals that might impact on the system. And then no feedback is required if you're living in a perfect world, but our world is not perfect, so we do need feedback. Feedback control systems are described in terms of block diagrams typically. So the block diagram consists of a box. So a box like this with inputs and outputs, and these boxes could be linked together. So the output of one box could be an input to another box. And these boxes can take actions, and measurements can also be taken from the box. And these actions and the measurements are called outputs, and they're indicated with an arrow leaving the box. And then a box can also receive information from outside of the system or from other boxes, and those are called inputs. So to look at the structure of a typical feedback control block diagram, it consists of the following components. You first have a process or a plant that you want to control, and this is not like a pot plant that you put in the kitchen on the windowsill. It will hopefully become clear as I go on what we mean by a plant or a process there. The plant has some outputs that you want to control typically, and it might have some other outputs as well that you just want to observe. There's some sensors which measure what these outputs are, and you feed it back. This is like closing the loop. You feed back these measured plant outputs. You compare that with what you want the outputs to be, so the desired outputs, and the controller will then figure out what controller commands to give. Sorry, let me just run down there. The controller will figure out what commands to give to the actuators, who have to, and the actuators have to implement the controller commands, so that the plant inputs will drive the process outputs towards the desired output. So the main idea is to make that and this the same. Yeah. Now, to take a human body analogy of this, you can think of the plant as the body. So there's the process. You can think of the sensors as the sensors that the humans have, like the eyes and the ears, and you feed back this output. You compare it to desired output. This is processed in the brain. So the control system you can think of, or the automatic controller is the brain of the system. And the actuators are like the muscle that has to drive whatever the body wants to do towards the actual output. compare that to a desired output. This microphone is on the wrong side for me to talk that way. So we were talking just before for the presentation about the distinction between maybe automation and control. And control is more about the brain of the system, the automatic control, and the automation would be what you need to make the control system actually work, like the actuators, the sensors, also the platforms on which you implement, the way the platforms are connected to each other and to the sensors and so on. So I'm going to talk about automatic control system and essentially this feedback loop. Now to give you a sense of the breadth of the field, I'm going to take the IFAC technical board and break the technical board down into its different coordinating committees and also show you what the technical committees do under those. So IFAC's technical board has got 9 coordinating committees, 4 of them are theory based, and then there are 5 application orientated technical committees, coordinating committees with a number of technical committees under them. So the first one is mechatronics, robotics and components. And the technical committees under this coordinating committee is mechatronics systems, robotics and human machine systems. Then there's a coordinating committee, manufacturing and logistics systems, where we have a number of technical committees, manufacturing plant control, manufacturing modeling and management and control, enterprise integration and networking, and then large-scale complex systems. Then there's one process and power system. So this is where my research area is based in this coordinating committee. We've got chemical process control, mining, mineral and metal processing, power and energy systems, fault detection, supervision, safety of technical processes. And then there's the technical committee on transportation and vehicle systems, which includes automotive control, marine systems, aerospace, transportation systems, intelligent autonomous vehicles. And then there's one on bio and ecological systems, control in agriculture, biological and medical systems, environmental systems and biosystems and bioprocesses. And then the last one is social systems, where we look at economic, business and financial systems. Also the social impact of automation, control of smart cities and control education. And so the purpose of this slide is to give you an indication of the breadth and also to say that these systems will work less well or not at all if not for automatic control. So that brings me then to the examples that I'd like to present. I'm first going to talk about physical engineered systems and in particular mechanical systems with an inverted pendulum, a quadcopter and an aircraft. Then I'll talk briefly about electric power systems and then grinding mill circuits. And then I've got one example of non-physical engineered systems where I'm going to talk about personal finance. There are many others that one can also possibly talk about. And then non-engineered physical systems, glucose homeostasis and also HIV/AIDS therapy. So let's get to the mechanical systems. The first one I want to talk about is the fact that automatic control can balance an inverted triple pendulum. So let's have a look at a little video. So this was done in Professor Andrew Kugi's lab at the Technical University of Vienna a few years ago. So the way the system works is you've got a motor that's connected to a drive belt which moves this cart up and down. And then there are sensors which measures the position of the cart and then also the relative angles of each of these pendulum components. Right. Now in our final year we've got finally a project which is the equivalent of 4 undergraduate final year modules. So the plant in this case, so the system that you want to control is the pendulum system. There are 4 outputs, the cart position and the 3 pendulum angles. And these encoders are 2048 increments per rotation, so they're very accurate, and they've got a wireless connection to the hardware on which the control system is connected, so there's not much friction, as you could see. And the motor, the input is just a motor connected to the cart by a drive belt. And for control guys in the audience, this is the block diagram. So there's the system. You've got the outputs, which are fed into an observer. The inputs also fed into the observer. You estimate a trajectory, compare it to what you want it to be, and then do control based on that. And there's also a feed forward term. So feedback control, something has to happen first before you can feed it back. But with feed forward control, you can anticipate, if you have a very good model, what's going to happen, and then take some corrective action before the feedback actually gives you the information. So that's the one mechanical system. The other one I briefly want to show you is this, that automatic control can make athletes out of quadcopters. So just have a look at this video. And
has a racket strapped onto its head with a sweet spot roughly the size of an apple, so not too large. The following calculations are made every 20 milliseconds or 50 times per second. We first figure out where the ball is going. We then next calculate how the quad should hit the ball so that it flies to where it was thrown from. Third, a trajectory is planned that carries the quad from its current state to the impact point with the ball. Fourth, we only execute 20 milliseconds worth of that strategy. 20 milliseconds later, the whole process is repeated until the quad strikes the ball. Machines can not only perform dynamic maneuvers on their own, they can do it collectively. These three quads are cooperatively carrying a Skynet. They perform an extremely dynamic and collective maneuver to launch the ball back to me. Notice that at full extension, these quads are vertical.
so this is what we have. Is we got the plant is the quadcopter. The inputs are the speed of these four motors. And then the outputs are the angular velocity of the vehicle, the position, and also the orientation in terms of pitch, roll, and yaw. There are 8 cameras in the roof of this arena, which very high-speed cameras, which tells the quadcopter controller where the quad is and what its orientation is. Okay, so with that, I'd like to move then on to modern aviation. And hopefully I can convince you that with automatic control we can have modern aircraft, and without we might have something like this. Okay. So I'd like to have a look at the evolution of aviation from 1903, when the Wright brothers flew their first Flyer 1 aircraft. This was the first powered flight and also the first aircraft capable of sustained controlled flight. It's not an airliner, so the heading there might be a bit wrong for this first example, but for the others it's correct. The next big advance that came in airliner type aircraft was the Boeing 247, where the first autopilot was introduced. Then the next big advance came with the Convair 880 in 1959, where the first so-called handling qualities controller was introduced. And this was necessitated by the fact that this aircraft could fly a lot faster and also a lot higher than the aircraft it came before could fly. And for a pilot, it's difficult to fly a plane when the dynamics change all the time. So the faster you fly and the higher you fly, the more the dynamics is different from what they're used to. So they introduced a handling qualities controller to make the response to the pilot commands feel the same over the entire flight envelope. So whether you're flying fast or slow or high or low, the response to the stick movements felt similar. The next big advance was in airliner control was in 1982 with the introduction of the Boeing 767, where the first flight management system was introduced. And with this system, you could just give it like GPS waypoints, and the aircraft would fly to those waypoints. This greatly reduced the workload and fatigue of the cockpit crew. So airliners then reduced the number of crew from 3 to 2. So like we have today still, you have a captain and a co-pilot, or a pilot and a co-pilot. And then the next big advance after that was shortly after this 1982 was the Airbus A320, which was the first fly-by-wire aircraft. And this also made it possible then to introduce safety systems so that the pilot couldn't do something that he shouldn't do unless he overrides all the control loops, of course. So if we look at the aircraft system, what is the plant? The plant is the aircraft. The output typically is the attitude of the vehicle, so pitch, roll, and yaw, and also how high it's flying, and then the airspeed. Those are like the main outputs. There are lots of others as well. Then the inputs are the control surface movements, like the ailerons on the wings, the elevator, and the rudder angles to try and achieve the right attitude for the vehicle, and then also the thrust of the engines. So if you look at the Wright brothers Flyer 1 in terms of a feedback block diagram, there's the aircraft structure as the plant, the aircraft state is the output, and the pilot in this case did all the sensing. So you could see where you're going, and you could feel with your vestibular system what the orientation of the vehicle was. So, and then the pilot got those signals, went into his brain, and then he told his hand to move the stick or warp the wings depending on what he wanted to do. Then with the Boeing 247, an autopilot was introduced, and also there were now sensors measuring the attitude of the aircraft. So the aircraft state was measured with sensors. You fed that back to a desired state. These went into the autopilot, and the autopilot then decided how to move the control surfaces to give a desired aircraft output. Then with the Convair, in between the autopilot and the aircraft structure came this handling qualities controller. And so what happened there is the aircraft state is measured with the sensors. You feed the sensor information into this handling qualities controller, also into the autopilot, and compare that with compare where the aircraft is now to what the pilot wants it to do. The autopilot gives control inputs to this handling qualities controller, and that will then decide how to move the control surfaces of the aircraft. The flight management system sits outside of the autopilot, so that you enter the route here. The flight management system will then decide what the desired aircraft state is, give that information to the autopilot, and the rest of the structure is the same as on the previous slide. So you've got the control inputs to the handling qualities controller, control surface movements, and then hopefully the aircraft state will go towards the desired aircraft state here, and it will follow the route that the pilot wants it to follow. And then where does the fly-by-wire technology come in? It comes in here with the handling qualities controller. This is now then completely digitized, and it resulted in better control of the control surfaces. And then also you could, for instance, say that the control surfaces are not allowed at this particular altitude and this particular speed to go into a position where you can stall the aircraft, for example. And how is it possible for that German pilot to fly the plane into the Swiss mountains? I don't know if you remember that case of a few years ago. It's possible because the pilot can still override all the controls. Yeah. Right, so that's the mechanical system part. I know there are a lot of electrical engineers in the audience and people who know a lot more about this subject than I do, but I'd like to give you just a brief overview from an automatic control point of view. So what we say is that with automatic control there's going to be power, and without there won't be power. So that's the bottom line. And just a few observations in terms of electric power systems. They're facing increasing stress due to fundamental changes in supply and demand technologies. One can think in terms of distributed generation, for example, renewables being introduced, where the supply depends on the weather, and the weather might change, and you have might have a big change in the supply if you've got a big part of your system as renewables, and then it's difficult to match the demand and supply. Also, you require greater flexibility, agility, and the ability to dynamically optimize the grid operation in time frames that are short, that are too fast for human operators to handle. So what are some of these automatic control loops that are active in a electric power system? One gets generation control at the system operator level, where the controller has to manage to match the supply and demand. If you don't do that, the frequency drops or it goes too high, and then it might lead to generator trips, and then you have a blackout. One also has power control at each generator turbine set. Then also automatic voltage regulation to make sure that you have the right voltage and reactive power in the system. And then also on top of these automatic voltage regulators, there are power system stabilizers to stabilize the power angle. So if any of these 4 types of control systems were to fail, let alone all 4, you'll get a rapid deterioration in the stability of the system, and then eventually a complete blackout, which might take a long time to recover from. Right, then the next physical engineered example I'd like to talk about is industrial example, something that I've worked on a lot, and I see Quibus from Mintec here as well. He knows the system very well. Grinding mill circuits are part of a chain of processing in mineral processing and metallurgical plants. So I just want to quickly run through this. You start with run-of-mine ore. This is the ore that comes from the mine. You might crush it to make it a bit smaller. It goes into this grinding mill, which turns around at a particular speed to try and reduce the size of the ore that comes in to a size where the actual minerals that you're interested in, the gold or the platinum, are actually exposed, so that you can then treat them in a separation circuit, either flotation or leaching, to separate them in a concentrate which contains the valuable minerals, and also in terms of a tailing, which is the stuff that you would throw away and maybe reprocess in 20 or 30 years' time. The concentrate is then further refined by extraction technologies like electrometallurgy, pyrometallurgy, and solvent extraction to provide the actual metal that you're interested in. So what I briefly want to share with you is a single stage grinding circuit like this. It gets the grinding mill here gets fed with run-of-mine ore and some steel balls and some water. It goes inside the mill turns around at a particular speed, and when the particles are fine enough, they actually leave the mill through a discharge grate here, discharges into a sump. You add some water, where you dilute the slurry that comes out of the mill. This gets pumped up to a hydrocyclone, and then the cyclone would split the fine particles and the coarse particles. The coarse particles go back to the mill. The fine particles go to the separation circuit for further processing. So what is the plant here, and what are the control actions, and what are the outputs? That's what I'm driving at. The plant is the grinding mill circuit. The inputs are the feed rates of the ore, the balls and the water, and also the speed at which the mill turns. You can, on quite a few plants, you can change that. And also the pump speed. So how fast do you pump the material to the cyclone? You can also change that. Then the outputs are the product size. So the liberated minerals, the size of the particles, and also the density, maybe also the throughput, how quickly do you process material through the circuit. The mill filling, how full is the mill power, the power that's drawn from the mill motor, and also the sump volume. Now these two outputs, so the sump volume, the sump is just like a tank. If you fill it up, it's going to overflow if you don't have a fast enough outflow from the tank. So these two loops are open loop unstables. You have to control them, otherwise the system will be unstable. And then you will typically control product size and maybe throughput if you've got enough control actions. So the feedback loop looks like this. You've got the plant with these outputs, the product quality, for example. You measure them with sensors. You feed this back to some desired outputs. The controller will then decide how to change these actuators, the pump speed, the valve openings, the mill motor, and the pump motor, in order to drive the plant towards the desired output. So that's a feedback block diagram of a grinding mill circuit. And this concludes then my examples for physical engineered systems. The typical ones that we would talk about maybe in engineering disciplines. So just some concluding remarks on physical engineered systems. Automatic control for engineered systems is essentially about taking the person out of the loop and replacing him or her with an algorithm. And what are some of the rationales for doing that is algorithms can run on computers faster than, or closed loops faster than human operators can. Computers can run continuously without fatigue. They don't take bathroom breaks, they don't have to go and make coffee and so on, they can just keep on running. Putting humans in the loop might be impossible or very dangerous for them to do. So you can't really put a person on a rocket and tell that person to steer the actuators of the rocket, for example. Systems can be miniaturized, so in your mobile phone there are quite a few control loops, and you can't put a person inside the mobile phone to do some control there. The output is your current net worth, assets minus the liabilities, and then the inputs, the investments made, so from your savings, income minus expenditure, also fees that you might pay on the investments, returns that you might get, and there might be a host of other inputs as well that you can probably think of. Tax, yes. Might think of that as a fee, maybe. So what can a feedback loop look like in this case? So that there's the plant, the output is the current net worth, so you can easily measure that on a computer. You feed that back to what you want the net worth to be at a particular time. Timing is obviously very important in investment context. The controller could be the investor or the financial advisor. Will give control commands to the actuators. Now what are the actuators? One is the money generated, and then also the asset allocation. What do you invest in which asset class? Because that's the biggest determinant of how your portfolio is going to do. Obviously there are a lot of constraints on these actuators. You can only earn so much depending on your earning potential. For example, asset allocation, the investment advisor can maybe tell you what that should be. But what I'd like to illustrate here is that you can take almost any interaction with the system or between two human beings, the professor and the student, or girlfriend and boyfriend, and work out the control loop for that. See what are the desired outputs, what are the real outputs, and most difficult with human interactions, what are the actuators that you can actually move around to achieve your outputs. Okay. Right, so that's the only non-physical example. Now I want to move on to a non-engineered physical system, and particularly going to look at some examples of what happens in the human body. So the first one is I'm just going to briefly talk about the main concept of homeostasis, and then give an example of a particular feedback loop. So without automatic control in the human body, you're going to be dead, and with it you'll be very much alive, hopefully. Okay. So what is homeostasis? Homeostasis is the tendency to resist change to maintain a stable, relatively constant internal environment. And that is the same as saying doing negative feedback control and regulating the output at a particular value, and doing disturbance rejection of whatever disturbances there are. So what are some examples of homeostasis or feedback control in the human body? Just listing a few here. One is temperature control. So the temperature has to be around 37 degrees. If it goes too far above or below, you either have to get intervention or you might not survive. Blood pressure control is another one. And the one I want to expand upon is this control of the concentration of blood glucose. So if these control loops and thousands of others in the human body were to fail, it can lead to serious illness, and if you don't get help, then it could lead to death. So let's look at the first one. This is the glucose homeostasis loop, natural glucose regulation. So this is with a person that is healthy and can regulate glucose. So what happens is that you eat something, so you've got carbohydrates that you consume, that will increase the blood glucose levels. There are some cells in the human body, including in the pancreas, which would detect the increase in glucose and then produce a hormone called insulin, which you might have heard of, which helps especially the liver and the muscle and the fat cells, but other cells in the body as well, to absorb glucose. So this is the energy that the body runs on. Inside these cells, these glucose molecules congregate together in very big molecules called glycogen, and then the energy is, so to speak, is then stored in the liver and the other cells. That action of absorption of glucose into the cells reduces the blood glucose level, and then you've got a lower blood glucose level. When the blood glucose level goes too low, the pancreas will produce glucagon, and glucagon has got the reverse type of action. It stimulates these glycogen congregations of glucose molecules to break down into glucose and then release it into the bloodstream. So from a control point of view, you can think of insulin as a control action to reduce blood glucose levels, and you can think of glucagon as a control action to increase blood glucose levels. So what is the plant? The plant is the blood glucose pool. The outputs are the blood glucose concentration, and then inputs, it's the two hormones produced by the pancreas, glucagon and insulin, and then other factors which play a major role in the blood glucose levels are the meals that you eat, the exercise that you do, and the amount of stress that you are under. When you eat, obviously you get an increase in blood glucose levels. When you exercise, the levels go down because you're actually using energy in order to do the exercise, and also when you're under stress, you use obviously more energy. So what does the control loop look like? So this is there's the blood glucose pool. That's a plant. There's some external inputs: the meals, the exercise, and the stress. The inputs to this plant is the glucagon and the insulin. Output is the blood glucose level, which you then compare to what you want it to be, and then the pancreas will react based on the difference of the blood glucose reference and the feedback that it receives to go and increase the glucagon or insulin depending on the situation. So somebody with type 1 diabetes, this link is broken. So the type 1 diabetic, the pancreas doesn't provide sufficient insulin to actually get the blood glucose levels down. And if it's too high for too long, serious illness will result and then eventual death. So a person with type 1 diabetes lose the means of decreasing blood glucose levels. So what can be done about that? You might know of this. The pancreas is still producing glucagon, so that's fine, but what you need to introduce is something that will supplement the insulin, and this is typically done by injection. That's why we have a switch here. This indicates a switch, so it's a discrete action. You don't inject all the time. You only do it maybe 3 or 4 times a day, or depending on the situation. The measurement has also now changed. So the pancreas will continuously monitor the blood glucose levels, but obviously you're not going to be able to do that as a human being. So you have to prick your finger and then measure the blood glucose content. You compare that to what your doctor tells you it should be, and then you decide how to when to inject insulin, and also doctor will tell you what type to introduce. So this is a typical injection times. When just before you go and eat, you know there's going to be a glucose spike, so you inject the insulin to make sure the spike is not too big. And typically this will be done 30 to 15 minutes before, depending on the type of insulin that you actually use. So before breakfast, before lunch, before dinner, and maybe at night time as well. So this is the current state. People might differ in terms of how they do the injection, but this is the current state of the art. This is the present in terms of research, but also the future. So you're going to have, using an engineering term, a glucose pump installed in your body, and a lot of people have that already. So there's the glucose pump. It's controlled by some controller which tells the pump when to inject and how much. You also get continuous glucose measurements, which can also be installed. It will send a signal to some little computer here to tell the computer what the blood glucose levels are. And then once you've got an actuator, so this will be the actuator, and this is the sensor. Once you've got those two, and you can figure out the model of the system, you can actually implement a controller, which is called an artificial pancreas system. And this has already been done. There are field trials. This is an IFAC colleague of mine, Frank Doyle, who's now Dean at Harvard University of Engineering. And they actually busy with field trials all over the world, clinical trials. And once that's completed, you probably can go to a shop and buy the system. Right, so the next one I'd like to talk about, and this is my last example, is HIV/AIDS therapy. So what is the plant here? Again, there might be different ways of interpreting this, but the plant that I'm considering is the immune cell, the CD4 cell that's being infected, and looking at the life cycle of HIV as the virion penetrates the cell and actually produces copies of itself. So the plant is the HIV Lifecycle. The outputs are the CD4 lymphocytes, or also known as CD4 plus T cells or T helper cells. These are the cells that identify pathogens in the body. And once the pathogens have been identified, you call in the troops, and the killer T cells will go and kill the invader. So without them, your immune system doesn't function properly. And then the other output is the viral load. Inputs are the drugs that you can take. There are two classes of drugs, reverse transcriptase inhibitors and protease inhibitors, and I'll talk a bit more about them in the next few slides. So that's the plant. What does the control loop look like for this? Now this is quite a busy slide, so I'm going to go over it quite slowly. So the patient is the model. So, or the plant or the process. The outputs are the CD4 cells and the viral load. You measure that in some way, and the measured CD4 count and the viral load is compared to some reference value, and the controller would decide how much of which drug to take in order to reduce the viral load and also increase the CD4 count. Now there are some other boxes here that we haven't seen before in this presentation. The first box is disturbances that impact on the model and the patient, and these are things like adherence to taking the medication, resistance to medication that could also happen, some environmental and social factors that might impact on the patient's ability to respond to medication, and then other virus sources, because we're only going to look at a single compartment type model where the virus actually, where you measure the virus in the blood, but there are other places for the virus to also hide away. Then in terms of the measurement, you've got assay detection cutoffs. You can only measure up to or down to a particular point and not below that. There might be some noise in the measurements. And for the actuators, the drugs could be expensive, they could not be available, it could be toxic, and there could be a limited therapeutic range as well for the drugs. And then some disturbances on the actuators, its efficacy variability, depending on the patient, the drugs might not be so effective, and the drugs might also interact with each other. So there's a lot of things to consider when you think about a HIV control loop. So what is the model that you see that little red block there? That we're now talking about the model. We're talking about specifically a three-dimensional single compartment model. Single compartment talks about the immune system interaction in the blood plasma. So that's all we're talking about. We're not talking about how it interacts with virus in the tissue. And the states that we look at is the healthy CD4 cells, the infected CD4 cells, and the virus. And you can think of the model, I'm not going to show any mathematical equations in this presentation, but you can think of the model working like this. You've got a healthy cell infected with a virus at the infection rate beta, produces an infected cell, and the infected cell then is the source term for the virus. So the infected cell produces more free viruses, and the healthy cells are produced at the rate S in your thymus or in your bone marrow, and all these the healthy cells, the infected cell, and the virus die at a certain rate, so which occurs naturally. So this is the model. It's a type of a population or a predator-prey type model. For those of you who might have looked at that. The HIV lifecycle is as follows. You've got a HIV virion which binds to the CD4 receptor on a CD4 cell. That's why it's called a CD4 cell. It's got a CD4 receptor which HIV specifically targets. It then enters the cell, converts single-strand RNA to double-strand DNA with a process called reverse transcription. It then enters the actual nucleus of the cell, becomes part of your own genome. So once that's happened, you've got HIV, and there's no way of getting rid of it. And then it uses the machinery of the host cell to make copies of itself, and functional viral proteins are cleaved by a viral enzyme called protease, and that then results in the production of new virions. So why do I show you the life cycle? We're going to specifically look at reverse transcription. There's a drug that tries to prevent this, and there's another drug that tries to prevent this protease enzyme from being effective. So what is the actuator for HIV treatment? There's a treatment called highly active antiretroviral therapy, or HAART, which has changed also in South Africa HIV from a death sentence to a chronic illness. So many people are HIV positive, but they lead normal lives due to the medication that's available. The type of drugs that you get is the replication-based drugs, which I'll talk about in a short while, which disrupts the virus replication process. And then the other one is immune-based therapies, which expands the CD4 T cell pool by direct lymphocyte transfer. So we're going to talk about the first one. So replication-based antiretroviral drugs include reverse transcriptase inhibitors, which tries to prevent this reverse transcription from happening. And then protease inhibitors tries to prevent this process from happening. So those are the two categories of drugs, and typically we take more than one of each in order to make sure that the virus doesn't replicate. What are the measurements? So the model outputs are the CD4 T cell count, and the viral load are measured from blood samples. These measurements are invasive, they're discrete, and they're also infrequent, which is, from a control point of view, is not a nice thing. Okay? We want continuous measurements. Discrete and infrequent measurements result in aliasing, so high frequency behavior you might miss, and you might see it as low frequency behavior, for example. And also measurements are single compartment only. You only measure what happens in the blood, and you don't measure what happens in the tissue. That's even more invasive if you take tissue samples. Then when do you do these measurements? At the time of diagnosis, and then every 3 to 4 months thereafter. So a person has AIDS when the CD4 count goes below 200 cells per microliter. And then the measurements that you do are typically done by the flow cytometry technique, and the cells are distinguished according to their surface markers. We're particularly interested in this CD4 cells. So if you were to send a patient's blood to a pathologist, this is what something that you might get back. And we got 2 patients here. This is the first one. We're looking at 2 numbers, specifically the CD4 lymphocytes. You can see this one is 238. The normal range is 358 to 1,200 something. And this person has got HIV because there's a viral load, but it's very low. Should be between 0 and 40. This one is 53, but it's still okay. So this person is probably leading a normal, healthy life on the correct drug therapy. Patient 2 has got full-blown AIDS. So this is a CD4 lymphocyte count is 30. So there's almost no immune system left here. And you can see the viral load is very, very high. What are the control issues here? So ARV therapy from a treatment of HIV infection point of view, for those of you who might know control, is a control of a nonlinear time varying dynamical system, which is the patient, with constrained control, so that those are the drugs. They can operate only in a certain region. And you also have discrete and irregular actuation, so the actuator can only work in a discrete way, and the sampling of the output, we have to take blood samples, obviously also infrequent and discrete. So this is a difficult control problem to deal with. So finally, the simplified control loop. So we got the model as the patient.